All right, and greetings and welcome, friends, to our Thursday edition. Hope everyone's doing well. Oops, that's not what I wanted to do. Let's do this. Okay. Hope everyone's doing well. And things are up to speed. We are in week 4 right now. So just as a reminder, homework 3, I put up and it's due Tuesday. So at that same point, quiz 3 will be enabled, same deal. You'll have the full day of Tuesday to turn in the homework and full day to do the quiz. So please be sure of that. And I think that's where we're going for now. Talking a little bit about energy and power. And last time I did the video late last time. So if you haven't already, take a look back at Tuesday's class video. It's up. I posted that. Let's see, I must have done it Tuesday night. So it got posted Wednesday morning. So if you haven't checked that out, go ahead and take a look at that. Talking about energy and power and transfers of energy and hybrid cars and all sorts of good stuff like that. So we're back here now, and I'd like to go into a little bit more on I mentioned in class last time that the kinetic energies of things can be even down to microscopic, what I call microscopic, but that's not a very good word for it. I'm thinking as a scale, I'm thinking on the atomic scale, and that is well below what we would be able to see. So the word microscopic is not completely appropriate, but atoms and other what we call quantum mechanical objects, quantum objects, really tiny, small things. Energy works really well for them as well. So we're going to try and take a look today at what energies look like in materials, gas, liquid, solid, and then what happens when we think about heat and temperature. And I talked a little bit about that last time. In terms of the difference of heat with respect to temperature. So let's go ahead and get started, and let's talk a little bit more about that. So I think you have enough to complete the homework questions as of now, in terms of what types of things you would need to have known to answer the homework question. So I think that's all set. I'm going to start on atoms and energy in atoms. So the word atom is well, it's derived from the Greek, and or maybe it's derived from the Latin. Anyways, I'm going to say it's derived from the Greek, so that's what we're going with. The idea of the atom is that it's this small indivisible piece, and I think that's what atom, the root word essentially means, is that it's undividable up. You can't break it apart into anything else. we have since found that that's not true. But ultimately, these are the building blocks of all materials that we are able to observe and use and work with in the universe. So yes, you can go a little further and say what makes up an atom, and you can talk about a nucleus and electrons around it and things like that. And you can go even further and further than that. What we're going to talk about today is a bit more of behavior of the atoms themselves rather than the pieces of the atom. But basically, these are the building blocks of materials, and anything that has a structure to it, or something like a gas which fills a container, is made of atoms ultimately. So what we're going to do is take a look at some of the phases of matter and see what we come up with as we try to transfer between them. So the building blocks, we're going to come up with basically the three states of matter. Okay. And I'm by no means am I saying these are the only states of matter that exist. These are just the three most common ones. There are always, extra things you can do. You'll often hear someone speak about the fourth state of matter. Well, there's probably about 20, 15 to 20 states of matter that can exist, but they don't necessarily exist. These happen to be the most common three for us, as well as another one called plasma. And there are other states of matter even past that. So it's not like these have these ones have written the book on it or anything. It's just the most common ones. It's like what Newton would have told us about forces. Well, forces are pushes, pulls, and they do things, and it's based on observation. Well, these are the three most common things that we see. So this is based on our observations. Now, what's perhaps a little interesting here is just by way of classification. We can take a look at what the structures of each of these things looks like and try to group them a little bit. Well, typically we would talk about both gas and liquid as being fluids. In other words, a fluid is something in which when you try to force it, there's a flow involved, right? So gas will flow. Well, you can't see the air in this room. No, you wouldn't be able to if you were sitting here either. So if I try to push the air, right, or if I try to bike through the air or somehow drive through air or whatever, the air flows around the object. And you may have seen stuff like this in if you've ever seen a wind tunnel or a smoke trail or something like that, where people are saying, well, what does the air look like as it goes around this vehicle or this airplane or something? So the fluid flow, and you'll know the same thing happens with liquids. You can pour liquids. Well, you can pour gases too. It's pretty great. So So what you can say about a fluid is there's, never mind. There's flow when you try to apply a force to it. So there's a component of something that's going to flow around, and that is the kind of defining trait of a fluid. A solid is what we've been talking about. When you apply a force to it, the whole thing moves together as a bulk item. And typically the structures of the solid is kind of what you would think about, kind of a lattice work. I've got this grid on the board, which you can maybe kind of see, but if I were to just draw a circle at every corner here and then connect them. All right, I'll just draw a 3x3 kind of matrix thing here. If I were to connect these with small lines, this is basically, and you thought about kind of rotating it around in 3 dimensions. So it came out this way, it went that way, that type of thing. So like this, right? Like your basic tic-tac-toe puzzle. I've left one off right there. If you think about that, that's essentially like a crystal structure. That's a lattice work of a solid. And when you push on a solid, I've left these other ones out here because I'm just considering it going further and further in different directions. But ultimately, when you get out here and there's a surface, right, you can push on the surface and it kind of dents the surface a little bit. But then through these lines here, which are representing the bonds between atoms, the force gets transmitted throughout the whole thing very quickly through basically a series of compressions, right? So when you push on something, and this is a pretty cool way to think about things, in my opinion. I am, after all, my specialty in physics is solid state materials. Well, if you push on a solid from one side, it takes time for the other side to realize that there's a force applied. Okay, so even in a for example, even in something like this, if I push on this side, there's going to be a small time delay before this side realizes, hey, wait a minute, I should be moving, because the force basically isn't transmitted instantly. There's time during which there's a compression of the atomic bonds here, which then moves into a compression here, which then move, and then it gets to here, and then this side goes, oh, I'm getting pushed, and then you see the whole thing go forwards. But in that small piece of time before that happens, this gets compressed a little bit, and then it starts to move, right? And so it's actually, while it's moving, it's kind of bouncing back and forth in a vibration. So it kind of is it's a soap bubble. If you've ever seen soap bubbles, this is what to me is so fascinating about watching soap bubbles. I could do it for hours. You watch them because when the person makes it and then snaps it off or does whatever you do, you watch the shape of it kind of go like that. And that's exactly, I just laugh because I'm like, yeah, that's how solids move, essentially. So that transmission is not instant. It takes time to go from one side to the other. Now, you can think about a characteristic spacing between the atoms, and I can see, or I maybe can see, I haven't made very big dots. So let me make these bigger. So you can see them maybe a little better than I drew it here. All right. Now you can define a characteristic spacing between atoms. And my atoms here are the black dots, the bonds are the lines that connect them, and I can define some spacing between them, right? Which on my board is just that big. Okay. Now what's interesting here is when I go back to my grouping, the gases and the liquids, which are characterized as fluids because there's a flow, solid, no flow to speak of, really. What's interesting is if I think about the atomic spacing of a solid and the atomic spacing of a liquid, actually these are very similar. They are very close together. So in terms of what we call, I'll give you a little bit of lingo here, the nearest neighbor. So if you're an atom, you just jump onto, suppose you jumped onto this middle one right here and you looked around. Well, you'd find a neighbor there, a neighbor there, a neighbor there, and a neighbor there. And they're all the same distance away. But then you look over this way right? And you'll find this one up here. That's a little further away. So that's not your nearest neighbor. It's your next nearest neighbor, right? It's like going to an orchard that has been planted in rows. Another thing I really enjoy doing is when you're driving on the road and you see one of these orchards, you'll see a spacing between the trees, right? It might be you're driving past and you can see a tree line going that way and a tree line going that way, and you're watching and there's a space between them. And then you kind of look a little bit forwards and all of a sudden the spacing's a little bit smaller, but then you can see that there's a way to walk right through without hitting a tree. And then you look that way and there's a space away. This is lattice spacing. This is great. This is what happens when you look at different directions, right? I would be looking, I could, for example, look this way. I could, for example, also look, it's hard to see on this one, but it would be kind of, woo, look at that, right along that line right there, right? I can see all the way through. Anyways, I'm getting off topic. But orchards, really great to go investigate what a solid atomic structure looks like at the small level. Anyway, liquids have very similar atomic spacings to solids. And that's surprising to most people because liquids flow and they have such completely different properties physically, even though it may be you're comparing something like an ice cube to liquid water. They are the same chemical element or same molecular structure, same thing, right? It's the same chemical compound. It's just that ice is very hard and liquid water is, well, not all the time, unless you are moving very high speed and trying to belly flop into a foot of water or something like that. Look, that the liquid actually has very similar atomic spacings to the solid. So by that categorization, gas is all the way away from that. Gas has like 10 times the atomic spacing of a liquid or a solid. So you could do that bigger. So if I said similar atomic spacing here, right, and I've circled the liquid and solid, now the gas is 10 times bigger than either one of these, and it's really quite fantastic. This is the reason that you know, in my mind, I'm going to jump straight to explosions, but you could think about boiling a pot of water on the stove, and this is the reason the lid starts jiggling, right? Because the gas, that, you know, you have so much liquid water in there, and the gas is taking up space, but there's not very much of it, but it's taking up all the rest of it between the top of the water and the lid. It's now a steam, right? It's a gas water. It's water in the gas phase. And so you can see the lids jiggling. If you were to rapidly shake a bottle of pop, soda pop, you shake it up, and then you could release that. You could, right, and that's the buildup of pressure, and it's the gas trying to escape and become its normal size, right? You're in both of these situations, you're kind of compressing it and keeping it smaller, and the pressure is building up very quickly. So a gas has 10x atomic spacing. Right, that's for the gas. All right, so I want to talk a little bit about atomic processes, which include how to get from one phase to another. We have water here on Earth. Most of the time, it is in the liquid form. You go, now's a great time to go to the mountains, and you'll find it in its solid form. And you can ski or snowboard on it and go, yay, and do all that stuff. Or you can think about steam and humidity in the air. That's water in its gas form. Also, I should say that the homonym, well, it's not a homonym, it has slightly different meaning, but vapor phase also means gas, if you think of water particularly, right? So gas. is also the same as a vapor. Let's see, I can write that just right below it. And of course, not necessarily of course, but you say the word vapor nowadays, and it may not mean that. It might mean a person, someone who does the vaping. It's a new thing for us old folks. Anyways, the technical term would be for a person, if you're inhaling a vape, if you're doing one of those vape things, it's not technically vapor, it's more of an aerosol. And so that's even another step between gas and liquid. It's like a combination of the both. So just like rain happens, there are droplets of liquid and even solid, like ice crystals sometimes, that hang in the air, right? In the gas. So they're small enough that they can just be moved around by the gas and the wind, as it moves around. They just kind of hang out. So you can have droplets of things, and this is the essence of the aerosol. It's a liquid that's suspended in a gas, basically. So you spray it and it comes whoosh, right? And it wets the thing, but it's propelled by a gas which is under pressure in the can. And effectively, our atmosphere is an aerosol. It's aerosolized because there are droplets of water. There are very small chunks of things, solid things like salt, especially floating around when you go down to the beach. I'll talk more about that later. But basically, you can have all three of these things happening at once, and that's pretty cool. I don't know, I'm not sure what else to say about that, but you can have all three of them going on once. All right, so there's a little bit on this. So let's first start talking about let's talk about the properties of each one first before we talk about how to get from one to the other. Yeah, no, let's not. Let's do it this way. Here's what I got. I know what I want to do here. All right, so this is going to go. All right, so I'm going to leave these up, except I already erased that one. No, I'm going to start new. That's fun. These whiteboards. You spend hundreds and thousands of dollars remodeling a building to get these whiteboards, and what do you do to wipe them off? You got these towels. I don't know. It seems like, shouldn't there be some technological thing that's like a big squeegee that just you push a button, it goes. I don't know. All right, so we've talked about the states of matter. Let's talk about how to transition between them. The states of matter also have another word called phases. So you may accidentally hear me, or you're not going to accidentally hear it. I'm going to accidentally say state transition. I'm going to use the words phase transition instead. So the word phase, when you're thinking about a phase transition, if I keep thinking about, well, I'm going to transition from liquid phase to gas phase, right? That means it's a state of matter transition or a phase of matter transition. Well, let's go do this. I'm going to make this here. All right, so I'm going to go back and we're going to put gas into liquid, and we're going to do solid. Like that. And now let's talk about how to get from one to the other. Now, in general, one thing that's very common for us to do I'm not sure if it's the most common, but it's one common thing for us to do, is to take liquid and make it into a gas this way. And two questions: how do we do that? And what's the name of that process? Somebody chime on in and let me know. Heat. Yeah, you add heat, right? You take your pot of water and you want to boil something, right? It's you're adding heat in order to cause this process, which is called boiling. Okay. Subsequently, if it wants to then go gas to liquid, the heat that you were putting in, you now have to remove. Okay, so this is back to that idea of heat being a transfer of the energy, not the actual energy itself. So when you heat something, yes, it's heated and it gets hot and there's hotness and heat in it and all that stuff, but not for a physicist. For a physicist, heat goes in and the temperature goes up. It doesn't hold heat. It has a higher temperature because the heat as energy has increased the kinetic energy of the little atoms and molecules that make up the liquid or gas that you're dealing with. Okay. So this process is known as boiling. Okay. There is another process that takes liquid to gas. For water, we have to put this maybe over a fire and wait for the whole pot of water to start boiling, right? So you can cook your food. However, the liquid to gas transition can happen at lower temperatures. And in those cases, it's called evaporation. And I don't think I'm going to fit that whole word here. Ooh, barely. Evaporation. So boiling is the process of bringing everything in a pot. You know, it's the whole amount of stuff that you have, the whole amount of liquid that you have. All of it's at the same temperature and it's high and it's all ready to become gas or vapor, right? It's ready to become in its gas phase. Evaporation is little bits at a time. And it happens at room temperature, right? If you take a glass of water and you leave it on the table for a couple of days, come back in 3 days, it's going to be gone, right? You're going to say, who drank all my water? Well, the atmosphere did, because basically it just evaporated and became part of the atmosphere. All right, so we need to apply heat to go from liquid to gas, and we need to remove heat in order to go gas to liquid. Here. And this process is known as condensation. Right, it's condensing. The exact reason that you wake up on a cold morning, pick any morning from the last 2 months, 3 months. It is winter after all, my daughter reminded me. She's like, well, yeah. I said, look outside, it's only 35. She says, yeah, it's winter. You got me there. Condensation, it's the thing that happens in cold mornings when there's moisture in the atmosphere, right? In an aerosol state, there's liquid water droplets and vapor droplet. You can't have droplets, and there's vapor water in the air, and it condenses onto a cold thing. Okay, a very unpleasant, not very unpleasant, but a rather unpleasant situation in which that happens. If you have ever lived on the East Coast, the humidity on the East Coast is outstanding. It is so humid on the East Coast. I happen to live in kind of the northeast part of the country, and during the summer months, there is so much water in the air. You go into a building and the building has air conditioning. Why air conditioning? Well, A, it's kind of hot because it's called a 90-90 day. 90 degrees Fahrenheit, 90% humidity. It's draining. It saps you. Okay, because you can't sweat really. So you go into an air-conditioned building. Why air-conditioned? Because it's hot outside, but also because air conditioning does what? It takes the humidity out. It actually dries the air out. This is why every time in your car, you push the defrost button, the AC kicks on and you go, well, I don't want it cold in here, but you do want the dry air. You want the dry air to come out and take the moisture. So it acts a bit like a sponge. Okay. So you go into one of these buildings that's air conditioned on the East Coast, you come out of the building, your skin is cold. It's the same temperature as in the building, which is maybe, 70 degrees Fahrenheit. You walk outside and it's 90 degrees Fahrenheit and it's 90% humidity and your skin is cold relative to the atmosphere. And all of a sudden you get wet. You're just standing there and droplets of water are forming on your skin because it's condensing on you. You have a cold, right? Your skin is able to remove the heat and allow the vapor and small droplets of water to condense on your skin. And all of a sudden you're like, it's like, I just walked outside, I'm all wet. Like, why, it's not raining? Yeah, it's not, because your body is below what's called the dew point and you are basically getting dewed on. This is a phrase that my children find very funny too. All right, so we've got this process going on. You can also go and look at liquid to solid transitions, solid to liquid transitions. Same thing happens, right? I'm applying heat going to the left. I'm removing heat going to the right. So if I think of the liquid to solid transition, that would be a situation of making ice cubes in the freezer. And that's exactly what I'm doing, freezing. Right, that's freezing. If I take the ice cube and I leave it out on the counter all day, what happens? Well, you know what happens. It's melting. Okay, so that's the back and forth processes for those. So those are the phase transitions. I will say that let's see. We're adding heat going this way. We're removing heat going this way. To do that. All right. My gosh, will you please be quiet? All right. Okay. There is also the possibility solid skips the liquid, goes straight to gas. Okay. This can happen also. It does happen in the snow, in snow conditions too. You will often see when the sun shines on, well, you'll see it definitely with the liquid too, but when the sun shines on snow, you'll often find that the snow doesn't melt, right? It just passes by the liquid phase and goes straight into gas phase. And when the sun's shining on it, there's a big input of energy, right? Well, or there's an input of energy on it, and it's absorbing, and then some of the atoms are just breaking off and going into gas phase. When a solid goes into the gas phase, this is called sublimation. I don't really have room for the arrow going back the other way. You can make gas turn into a solid. It's very uncommon, however. There is one chemical, there's one what's the word I'm looking for? I don't even know. There's one material that is very well known for this process, and it's carbon dioxide. Carbon dioxide is very rarely seen in the liquid form here on Earth. It does, however, exist very nicely in the gas form and also in the solid form. So when in the solid form, it's called dry ice, and it is a compound in which the solid phase exists at a slightly lower temperature than water's solid phase. Okay. Going back from gas to solid, it's basically, it doesn't have any really awesome name like sublimation. It's basically solidifying. It's no big deal. So anyway, carbon dioxide is well known for that transition. Water also does it. Most things will do this if it's a fairly natural occurrence that you would find it in the solid or liquid form here on Earth. Okay, questions at this point about the transitioning
I
and
thought gas to solid was superposition.
gas to solid? I'm sorry, say that one more time.
I thought it was called like superposition.
I don't think it'd be called superposition. It's basically solidifying. I think there's a technical name for it. It's not very impressive. I do know that. And that's probably why I never remember it. Let's see, gas to solid. I'll just ask the Google. It's called deposition, apparently.
Yeah, I got confused. That's what I meant.
Oh, super. Yeah, yeah. Deposition, not superposition. Yeah, that's good. Okay, so you were pretty much, you were way closer than I was. I don't know if that's a good or bad thing. Anyways. No, good. Yeah, that's right. Since we've got it, we might as well write it down. That's what I say. So going back this way. Deposition, it just means that you are literally depositing gas molecules or atoms or whatever onto a surface and then having the surface be cold enough that they just start forming a solid. Or you already have a solid slightly built up and you're just depositing more on there in order to become a solid. This is a very typical procedure when you are trying to build a crystal. So for example, what am I thinking of? So for example, silicon being a semiconductor, you want very pure pieces of it. This is how you make it. You literally deposit silicon atoms that you have heated and distilled out of, for example, sand. And then you just kind of slowly sputter it. You kind of take a little, it literally is called sputtering it. And the mental picture I have is of just like, right. And you just have the thing here and it just catches the atoms and then you all of a sudden you get a solid in front of you. So sputtering. Yeah. Anyway, so deposition is that process and we apply heat to do that and we remove heat to do that and off we go, right? Good. Okay, so let's talk about temperature scales. Let's talk about the temperatures at which these happen. I don't want to clutter this up, so what I'm going to do is take these out. Oops, I erased melting. That's okay. I'll write it back in there. Okay. We have a couple of temperature scales that I'd like to go through. They are initially based around water. Okay, water being essentially one of the most plentiful substances on Earth, one on which we are highly dependent, these transitions basically define our temperature scale. So what I'm going to do is actually start with the metric. I'm going to start with the Celsius, which you may know as the Celsius scale, which is actually someone's name. I don't typically call it the Celsius scale. I call it the centigrade scale. For me, much more descriptive. It's like a centimeter, right? It tells you exactly how many to expect. And there's a 1 centi means 1/100th of something. So a centimeter is about that big. It's 1/100th of a meter. Well, a centigrade is 1/100th of the thing here, the spread. So at the melting and freezing temperature in the centigrade, actually, I'm going to move this up a little bit. That is terrible. 0 centigrade. There we go. So melting happens and freezing happens at what's called the 0 centigrade temperature. Centigrade. Or if you must know it as the Celsius. It was named in honor of Celsius, who I believe was an astronomer, and I believe Swedish, Norwegian. Oh, I'm sorry, it's one of those places. Anyways, there you go. 1 degree of centigrade is the amount between the 0 and the 100. So boiling happens at 100 centigrade. Right? This is boiling of water, melting of water. It happens, or freezing of water, if you like. And so there are 100 degrees here. And so centigrade. Should you like to investigate what's known as the Fahrenheit scale? Also named after someone, Daniel Fahrenheit, one of the early investigators of what temperature means, trying to think about what does it mean if something is hotter or colder and how do we perceive it? Now, what I want to kind of encourage you to do is don't always trust your senses. Okay, we talked a little bit about the car example, where, for example, you're sitting in a car and the car suddenly accelerates and you get thrown backwards, but the car actually accelerated this way, but you got thrown that way, right? Same thing happens in a turn. You get thrown to the outside part of the turn, but the acceleration of the car is actually inwards because it is. So when you feel something, you go, oh, right, I feel chilled. If you have a fever, you take your temperature, but your temperature is hot, yet you feel the chills. So yeah, right? So your senses aren't always 100% right on. And you could go out on a day like today and say, wow, it's really chilly out here. Most people would do that because your skin temperature is typically around, you know, say 35 centigrade, which is around 80 degrees Fahrenheit. So on a day when the temperature is lower than your skin temperature, you feel cold. And likewise, on a hot day, you would feel hot because the temperature outside is higher than your skin temperature. But there are interesting variations to this. For example, I don't know if you've ever tried this. Take a pot of very hot, not boiling, but you know, maybe 80 to 90 centigrade water. Put your finger in it, or put your hand, your palm on it, and put your palm into a bath of ice water. And then switch them and see what it feels like. And sometimes, you know, when you get frozen, it's like getting a burn. You feel the same sensation of getting burned. If you've ever experienced something like a frostbite or sometimes you have, like I have skin stuff that has to get burned off, but they use liquid nitrogen, which is liquid air, very, very cold. And they, right. And then you're like, oh, this is killing me. And it's actually feels like it's burning, but the stuff is very cold. So your senses are a little bit different. Anyways, Fahrenheit. On the Fahrenheit scale, freezing, I think you're probably well aware of that for these days. Actually possible snow happening in the mountains today. If you live up in that area, please do be happy and safe today. This is 32 degrees on the F scale. So enjoy the snow if you get any today. Here at the boiling point here, well, here's an interesting question. Does anyone know the boiling temperature in Fahrenheit of liquid water?
Isn't it like 212?
212 is exactly what it is. Good job. All right, so here, just going to give you a little bit of look-see at this one. You can see there's a centigrade. There's 100 degrees between this, right? That's a difference of 100. Between 32 and 212 is a difference of 180. So the Fahrenheit degrees are slightly finer. You'd say, oh, well, is it 72 degrees today or is it 73 degrees today? You wouldn't get that on the centigrade scale. You'd say, look, it's either 27 or it's 28, and 27 is that's about room temperature. It's about 75-ish degrees, right? About there. And 28 is like 77 and a half almost, right? Or a little bit more than that, right? So it's about almost, you can see it's almost 2 degrees of Fahrenheit to every 1 degree. It's 1.8 of these to 1 of these. So when you convert between them, you just have a slightly finer grade of Fahrenheit temperatures. So they become decimals in the centigrade, which, I mean, ultimately you're not going to tell the difference between 33.1 and 33.6 centigrades. So nobody ever, it's like 33 or 34. So there's that. These are based on water. Okay, this is water boiling temperature. This is water freezing temperature, and there you go. Okay. One interesting thing you might ask is, why is water freezing 32? That seems fairly random. Which is a great phrase. My daughter would say that. That's so random. So why would this be 32? Well, when Fahrenheit thought of the scale, he tried to get the very coldest thing he possibly could get, and he called that 0. Again, I turn to some East Coast, I wouldn't say roots necessarily, but more experiences. I'm not actually from the East Coast, but I did live there. If you have ice on the roadways, and by the way, if there is ice on the roadways, be very careful today. No sudden movements. That's the trick to driving on ice. Just no sudden movements. All right, don't suddenly try to do something. Your car's not going to do it. When you want to melt that ice, do you know what they do? They drive around in a truck and they spray something on the ground, or they drop something on the ground, I really should say. Do you know what they drop on the ice in order to make it melt? No? Salt. If you drop salt on ice, it will melt the ice. Unless it's really cold. When salt water freezes, 0 on the Fahrenheit scale. That is the coldest thing Daniel Fahrenheit was able to get. Rock salt freezing in water is 0 Fahrenheit. So pretty cool. Pretty cool. Pretty cold, man. All right, so there's that. We do have one other temperature scale that I want to go through, and then I want to talk about some of the physical properties of these things. There's one other scale that I want to go through, and it's based on physics. Yes, finally, not something that's based on some random substance like water. I mean, sure, we have a lot of water. Can we think of something that doesn't have to be substance-based? Can't we all just get along without a substance? Sure, we can. And the reason we can is because we know what temperature means. All right. Temperature, if you remember, as measured by these devices, right, as measured by things that have, that's a thermometer or something. The temperature is a measure of the average amount of kinetic energy that these molecules have in the substance, okay? This is a kinetic energy. This is good, okay? Temperature, because we know what kinetic energy means. It's the motion energy, right? So temperature is it's kind of a measure and I used this abbreviation last time, the kinetic energy, the KE, measure of the average KE of molecules. Oh boy, can I fit that in here right there? Okay. Does that come through? Good. All right. So that's what the temperature is. Insofar as if the temperature increases, then the average amount of kinetic energy per molecule has increased. And what that means is they're going a lot fast. This is something that's very hot, except they'd be moving at more like 100 times faster than that, right? Oh, this is very hot, and this is very cold. Is there a way to think of a temperature scale based on the motion of the molecules? Well, for example, what happens when they stop? Kinetic energy is called the motion energy. Both of these temperature scales have negatives, right? Anybody who lived in Minnesota would know this. Okay, negative 30 degrees. Fahrenheit or centigrade, doesn't matter. It's freaking cold, all right? So these both go into the minuses. But when you think about the energies and the motion of a molecule, you can't have negative motion, right? It's either moving or it's not. So here we have a way to say, wait a minute, is there a lowest possible temperature? Yeah, there is. What happens when there's no kinetic energy? You can't have less than no kinetic energy. How can you be less than not moving? Right? I have no idea what that means. I also know that I'm kind of getting a little tired of the glasses for a sec. So, all right. Why would this be interesting? Well, having a lowest possible temperature, that's interesting because you can't go lower than that. That's a solid stop right there. You cannot go colder than this temperature right here. That's an interesting thing. Now, what about the other side? What about heating up? Can you go hotter? Then is there a roof? Is there a ceiling to the temperature? Well, yeah, kind of, right? Because of the motion and the speed being the thing that's kind of telling us what the kinetic energy is. A fellow by the name of Albert Einstein informed us that there is a speed limit in the universe, and that speed limit is the speed of light. So no molecule can exceed the speed of light. So there is kind of a ceiling on that. That, by the way, is insanely fast. We'll talk more about that when we hit relativity, but it's ridiculously fast. So it's way up there. All right. It's like the sun, the middle of the sun is somewhere in the range of like 15 million degrees. Okay. And it's kind of a normal star. It's kind of an average star. There are stars that are much hotter than that. Okay. So for all practical purposes, is there a ceiling to the temperature? Well, not really. Yes, technically, but it's so far up there that I don't know that we can ever really approach it that Yeah, right. No, it's not really. Anyways, but there is a floor, and we have approached the floor very closely. Okay. So this temperature scale, where is the floor? It turns out that the floor occurs way over here at minus 273 centigrades. That's the lowest possible temperature. All right. That's the lowest possible temperature. You cannot go below minus 273 on the centigrade scale. That translates to about 460 below zero on the Fahrenheit scale. Right? It's just not possible. Why? Because you can't have less than zero kinetic energy. You can't have less than no motion. So what happened then is somebody said, okay, well, let's call that zero because you can't go below it. And now we don't have any negative temperature. Yay! All right. So minus 273 is the lowest possible temperature. And that's known as zero on the, I didn't leave myself enough room to write the name here. This is known as zero on the Kelvin scale. Like Kevin, but with an L. Kelvin scale. All right, so zero on the Kelvin scale is the lowest possible temperature that you can go. Can't go below it. We have approached it. We have approached it so closely. You can never reach it though. You can't reach this temperature. And the reason is because cooling something off requires that you have something colder nearby. So if you want to, you're like, oh, I'm so hot, you dump ice all over yourself, and you go, oh, no, some of the heat leaving me and going into the ice. The ice was colder than me, and that's the way heat transfers. If you want to take the heat out of something, you have to give it something colder to go to, right? Remember, heat is a transfer of energy. Energy does not just disappear. It has to go somewhere. So in this case, the heat leaves the hot object, goes into a cold object. If we were to reach that temperature, though, that would mean we would have to have something colder than that for this heat to go into. But this is already the lowest possible temperature. Therefore, that is not possible. It turns out, however, that we've come very close. We've gotten, we people, science people, have gotten down to billionths of a Kelvin just above what's called absolute zero, right? So you can see on the centigrade scale that the temperature is minus 273. So all you got to do from the centigrade to get to the Kelvin is add 273. So melting of water in the Kelvin scale is 273 Kelvin. Boiling is 373. 273. 373. I'm not expecting you to know these numbers or anything like that, but I do want you to know there is the concept of having the lowest possible temperature, and it's not actually achievable. Pretty cool, right? It's like infinity. All right. So there's that. Now, I want to show you what happens when you do apply heat to something, but it doesn't change its state. Okay, so in other words, it heats up. What happens in between, right? If in between the freezing and the boiling processes, what happens when we're inside this temperature range? And I put heat into something and it heats up, but it's not suddenly boiling or whatever, right? I want to show you this. So I have this. All right, that'll work. And we'll put it maybe over here. Okay. See if I can get this thing. Nope, there it goes. No, it's going that way. All right, so right there is where it's going to stand. So I have this piece. This is it's a solid. It's a piece of material. I'm going to now add heat to it. This is currently at room temperature. I'm going to add heat to it with my flame here. There we go. All right, hopefully you can see there's a flame there. I'm not going to point it at the computer, but I am going to point it at this thing. And maybe you can kind of see what I'm doing here. Looking at the camera, you can see the orange yellow spot right there. I'm just going to keep it right about there. Oh yeah, look at that. That's really coming up now, isn't it? Oh, that's good. That's good. Okay, I'm going to turn this off. All right, so I just added heat. I just added a lot of heat to this point right here, to basically this point right here. Ooh, it's kind of toasty. Oh, yeah. Oh, okay. I can keep my hand on that spot right now. And just in case you're right, it's somewhere here. Right there. I'm putting my hand right on top of it. So yeah, it's toasty. I can feel it, but why isn't it? How come it's not so? I wouldn't put my hand in the flame, and I just use the flame to put energy into this thing. How come this thing's not burning the heck out of me right now? This is interesting. There's another thing going on. Oh, you can really smell the burning though. You can't smell it, I guess. I can. There's another thing going on, and that's what happens when you add heat to a substance and it does not change its state. It just increases its temperature. Okay. There are kinds of two things at work here. Okay. Number one is when I add heat to a substance, say I take a certain amount of heat, right? I'm going to take this much heat and I'm going to add it to this thing. Well, this thing's going to heat up, right? It's going to temperature is going to increase. But then if I take another thing, like, I don't know, these are metal holders. If I take this amount of heat and I add it to these, well, these things are going to heat way up. And I'm probably not going to touch these for several minutes because they're going to be so hot. Now, there's a couple of things going on here, right? Number one is not all materials heat up at the same rate when you put heat in them. Their temperatures don't increase all the same amount, right? You may be aware of this. Metals, if you heat a metal up, right? You put heat into the metal, the temperature goes up very quickly. Okay, so for even a small amount of heat, the temperature goes up a very large amount. I just put a huge amount of heat into this thing, but its temperature did not go up that significantly, right? I mean, it went up kind of significantly. You could see it was kind of reddish hot there, but it didn't go up to the point where it was just skyrocketing upwards, right? It wasn't so hot. Now, the other thing that's going on here is there's that coupled with the ability of the material to absorb and release heat. How well does that happen? So if I give a small amount of heat to this metal, it's going to absorb it and it's going to increase its temperature very quickly. Now, again, another East Coast story. These cold nights where you have to wait for the train because you're a commuter, and gosh, if you live in the northeastern seaboard, this is what you do. You commute by train. What do they have outside train stations? Benches for you to sit on. What are the benches made out of? Aluminum. Why not wood? Aluminum, when you sit on it, is very cold, but it heats up very quickly. And so you initially sit on the aluminum, you go, oh, that's cold. And then after a minute or two, you go, oh, okay, this is a little more bearable. And it's not too bad. So the aluminum takes in a small amount of heat, temperature goes up quickly. Wood, kind of like this thing also, does not do that very easily. It takes in a little bit of heat, or it can take in lots of heat, but only its temperature maybe go up a small amount. Okay, so things do not increase in their temperatures equally as you apply heat to them.
How come when you put an aluminum thing in the oven, it doesn't get that hot? Like you can usually still touch it, unlike a steel thing.
Unlike a steel, did you say?
Yeah, like when you use like a steel baking tray, it gets really hot, but when you use an aluminum one, it's usually like you can touch it pretty quickly.
Pretty quickly after you take it out.
Yeah.
Yeah, two things going on there. So those do have different rates of temperature rising and falling with heat. So even though they're both metals, they don't have the same, there is a slight difference there. The other thing that's going on there is the mass, like how much of there is there. Aluminum tends to be a lighter material, so it can form a baking tray, but it'll be a fairly light baking tray compared to a steel one, which will be heavier typically. So what's happening is, because the aluminum, well, let me back up. Metals in general will take in heat and their temperatures will go up quickly. But the opposite is also true. When I take a hot metal out of the oven, for example, and leave it to cool, it will cool off quickly because a small amount of heat leaves it and its temperature drops quickly. It will drop more quickly if it's a lower mass item. Okay, so you could imagine me taking this block here and cutting off, say, just this part of it right here and saying I got only 10% of the block. If I take that amount of heat that I just put into the main block and I put it into only 10% of the thing, well, that thing's going to heat up more quickly than the whole thing altogether. And so because steel is more dense, it has more weight to it. There's more of it to heat up. So it will take a little bit longer than the aluminum, though they should both be pretty quick. Once you take them out of the oven, they lose a little bit of heat. They should reduce their temperatures fairly quickly. But yeah, I would see the aluminum has a slightly better, slightly quicker rate than steel, and there's a lower amount of it in the tray. That's what I would say to that. Cool. That's a good question. Great observation too, by the way. It's that kind of observation that you can just kind of walk around and wonder, why is that going on? What's going on here? So yeah, hopefully that helps. All right, I want to show you what I'm going to do is, I know I've been talking a lot and not really writing anything down. But I know we only have like 5 minutes left, and I want to do this demonstration for you. And then so next class, I'll kind of do a bit more of a summary of what we just talked about in terms of what happens when you heat an object and how it holds the heat. Well, it doesn't hold the heat, I shouldn't say that. How it takes in the heat and then increases its temperature. I want to show you this. I want to show you this here. This is pretty nifty. So I've got, I feel like, gosh, there's this magician on Netflix, I think it is, Justin something or other. He's really good. But then you kind of wonder, well, how does he do all this with the TV? You know, is there anything going on? So here I'm going to try and show you. I'm really not making anything up. This is really a ring. There's really nothing. This is a ring that you could wear on your finger. I'm not, no fooling. Okay, I've got a ball on the end of a stick here. And you can see that if I take the ball, it will pass the ring. Okay, no fooling here. Now I'm going to increase the temperature of the ball with my flame here. And now the ball is not going to melt or anything because metals have such high melting temperatures. And sorry if I'm shouting, but this is kind of loud to my ear. I don't know if you're getting any of it. So just keep the rotisserie going here. Nice even burn. So get the ball heated up. And now we'll check to see, will it pass the ring? Nope. Won't pass through the ring anymore. It's hot, hotter than it was, right? Turn that off. Can't go through, won't go through. How about that for magic? Right? Now, just wait a little while. I've heated this ball and it has actually expanded. Oh, almost, it's almost there. Yeah, this is not something I want to touch with my hands right now. Metal is going to be extremely hot, right? I try to make good decisions about stuff like this. I don't always work, doesn't always work out. I still make the, you grab the thing out of the, what did I do the other day? I put one oven mitt on and I forgot, and I didn't put one on the other hand. Boom. Way to go. Good burn on your other hand. Yeah. Yeah. Yeah, let's see. Wiggling, it's almost there. It's going to eventually cool off and be able to fit back through the ring. Okay, try to keep us a bit on schedule here, but hopefully you'll be able to see that before we sign off today. Why? Why does this happen? It happens because of this right here. This is such a great model. It explains something like this. And the reason is why? Because of the dance floor. What's the dance floor? Go to the dance. Next time you go to a dance, you watch somebody moving like this, right? Right? You're going to dance, and there's people like literally crowded around you, and you can't do much more than that anyways, because people are like pressing into you, you're getting bumped from all, right? You're just trying to dance and have a good time. Now, when you get a little more energy, say, you go have whatever it is that gives you more energy, and all of a sudden your dancing becomes a lot more vigorous. Right? Now watch what happens. How much space do you have now? You take up more space. People start giving you more space. You start dancing, kicking, right? And all of a sudden there's a bigger space around you. But that's the same situation as this. When things heat, their temperature goes up, the kinetic energies go up. They're moving more, faster. They take up more room when they are moving faster. And so, yep, there it goes. There it goes. Look at that. Now it's back to its usual. This ball expanded because its temperature went up and its molecules were taking up just that extra bit more room, and that pushes the whole thing out. All right. So then it won't pass the ring, but now it's cooled off to the point that I can get the ring through. Right? Oop, come on. There you go. All right. Okay. Anyway, we'll do a little bit more of that in class next time. Don't forget homework. Oh, well, I erased it. Homework and quiz next Tuesday. Stay nice and warm over the next few days, and maybe dry. I don't know if you want to. And with that, have a great weekend. I will see you Tuesday. Thanks for coming.